This work is about the development of a miniaturized antenna for PocketQube. And the work is of Alessandro Vignato, that today is not here, but I will try to substitute him. Not possible, but I will try. Okay, so I don't have to explain what are CubeSats and the new trend of space economy, but a little parenthesis about PocketQubes. The standard is 5 per 5 per 5 centimeters. The maximum weight is around 250 grams. And this is a new trend. And I think it's a good trade-off for educational stuff, because it's not like for CubeSats that in years became more and more complicated in launch, operation, and test and qualification, and PocketQubes are like this new trend that allow us to send little experiments in space without a very intense qualification. So our project is the Redpill mission. We are a group of students born 2 years ago, and the Redpill mission is this 2P PocketQube system, and should be launched in 2026. Another interesting fact is that 𝗖cie and his list of hands-on projects add last year the PocketQubes. So we are selected for the Fly Your Satellite program that is also in collaboration with Alba Orbital for the PocketQubes management and launch and operation. Yeah, so the Redpill mission, it's a mission with the 3 payloads, we can say innovative payloads. One is like an heritage of our university, so the small debris sensor for confirmation of model of debris in low Earth orbits. Another, it's a tracking system with photodiodes and high-intensity LEDs. And the last one is a crystal that is a non-mechanical cover for telescopes. But what are the critical points of PocketQubes? For sure, the high failure rate. As I said, we cannot test it a lot. There are like plug-and-play technologies. We launch it in a very short term period, so development cycle is short. And the other fact is that we have very little space, so the redundancy, that is what saves us in space, it's not so it's not an easy way. So, which is one of the crucial roles, one of the subsystems that is important is the telecommunication system. And today we will talk about this subsystem and the subteam of our PocketQube for the telecommunication. Our communication system is pretty simple. We have a transceiver and an OBC that are like COTS components. To be really honest, the OBC is not a COTS component, but we develop our version, our bus for the PocketQube. But the interesting part is the custom-built antenna. This is like a trade-off, and this is an overview of the mechanism. On the left, you have the specification of the antenna. Probably you know that usually this type of antennas for CubeSats and PocketQubes are like built in-house. But we try to create also a deployment mechanism that could be a trade-off between mass, flexible positioning, and outcast mitigation and other constraints. And so on the right, you can see the integration that it seems very, very compact if you see it, because you have to imagine that there are 10 centimeters per 5 centimeters per 5 centimeters. So it's very small, and the antenna occupy a very small slot in the PocketQube. And another time, this is a trade-off between space and also efficiency of the antenna. These are the design requirements for the communication part, and also for the materials part. That should be an uncoated material to mitigate the outgassing, but also a resistant material. So another time, another trade-off. The team extensive search about possible materials, and in the end, after looking at the constraints, they find this rust-resistant spring steel. There is the X10 chromium nickel and 188 unimportant, and with a cross section of 0.2 per 5 millimeters. After this, after the material selection, we know the theoretical length of the antenna, but theory is a thing, practice it's another thing. So we tune it, and the final characteristics of our antenna are that they printed the PET structure and has this L-shaped cross-section to fix the antenna against the bottom PCB. The screws to mount it are three and 2 screws, and the antenna is hooked with a screw head. All the materials, all this design is compatible with the PocketQube standards. And also the bending radius is compatible with the flexibility of the material. What else can we say? We can say that we have a redundant system in our antenna design because the deployment should be fail-safe. So we have 3 redundant resistors that act like a thermal knife. So we have this nylon wire. The nylon wire keep in tension with the spring the antenna, and when we heat up the resistors, the antenna is released. Performance of the antenna. So we went to on 2 hills in near Padova, 20 kilometers distance, and we checked the communication and the losses in this 20 kilometer distance. So you have a table, and you can check it also on the paper about these specific tests. What were the results? Okay, so what can we say? That this mechanism is like an innovative mechanism. We were able to find nice trade-off between all the constraints and also our necessity to have a solid system for communication, because now communication, it means that you cannot find an object that is that small in space. And future milestones will be the vibration and TVAC tests in 𝗖cie HS facilities, that is the Center for Space Studies at our university, in which I structured. And yeah, this kind of tests, we are enabled to perform it. We already performed it with the previous design, but it will be interesting to understand if our antenna is qualified to fly in 2026. So thank you for your attention. If you have questions, I'm here, but I strongly recommend you to write to Alessandro, that is like the mind and also the arm of this amazing sub-team. Thank you again.